So today we are going to discuss about the transistor biasing circuit. This topic is prerequisite for the module 1, wherein we are going to discuss about the BJT biasing topic and small signal operation models for, that is both biasing and small signal operation for BJT and MOSFET. So it is essential to understand how exactly biasing is done BJT and what is the meaning of DC load line, what is Q point. Similarly, you need to understand a basic operation of MOSFET. So we need some basic information about this biasing and Q point DC load line with respect to the transistor. So let's get into that transistor biasing circuit. Okay. Main objective is to understand the biasing of a transistor for a linear operation and about Q point and DC load line. So here the main idea of a transistor is to use it as an amplifier. So it has many other applications. You can use it as a switch, you can use it as an oscillation, to produce oscillation as an oscillator, and other applications also you have. But amplification is most widely used, and for proper biasing only you can able to achieve faithful amplification, right? So biasing is very important. So you can see here this is one common emitter configuration is taken here. This is one simple circuit. So proper biasing is done here, right? So VBB is given to the base of the transistor through resistor RB, and this VCC is applied to the collector through RC. This is RB, this is RC, and values are given in this circuit for different parameters, like IB is 2 micro amperes, 200, and RB 10 kilo ohm, RC 220 ohm, IC 220 milliamperes, VCE collector to emitter voltage 5.6. okay, for a given VCC equal to 10 volts and VBB equal to, VBB is not given because it is variable. Okay, we have taken different values of VBB further later, so that it is not particularly shown. So for a particular value of VBB we get 200 microamperes, right? We are interested in current. Okay, it is current to voltage converter, right? So it's a current control device basically, so that is why we always talk about the input current rather than a voltage. So you can see the output characteristics of a transistor. It is drawn between VCE and IC for a fixed value of IB. Okay, so from the circuit we can see there is a VCE of 5.6 volts. You can see 5.6 comes around here, so you get one Q point. Okay, I hope you know how to draw the output characteristics for a given circuit. Okay, these are experimental results, right? Or you can have a graphical approach for this. This is a Q point, and you can see 20 milliamperes of IC you get for a particular value of VC. Okay, so this is what, right, Q point, and IB is equal to 200 microamperes. Okay, so this curve and this Q point we get only because we already considered few parameter values already, right? So like you have IB value changed from 200 micro to 300 micro. See change in IB. So there is a change in VCE respectively 3.4. So this is a new Q point, that is at 30 milliamperes. That is IC. Okay. Like you increase IB to 400 micro amperes, see here. So for 1.2 volts of VCE you get 40 milliamperes of current. You get 3 Q points, different Q points on different IB values. For different IB values we have three different Q points, right? And each time you increase the base current, collector current increases, right? Collector current increases, right? That observation you should make here. So collector current directly depends on IB. That is why IC is equal to beta times IB equation we have, right? So IC is directly proportional to IB. Increase in IB, increase in collector current, right? So whatever comes left of this, it is a saturation region, we know that, okay? So whatever comes here near the x-axis, that is a cutoff region. So if you combine these three cases, okay, these three cases, you get this, right? See, for IB values, different IB values, right? You get IC with 20 milliamperes, 30 milliamperes and 40 milliamperes respectively, and you can see you have three Q points, right? And this is a saturation region and this is cutoff region. Here you can see this is cutoff and this is saturation region, and this will be your active region, right? So amplifier always works in the active region, right? You need to place the Q point somewhere in the active region on the DC load line, right? So you need to know how you should draw the DC load line here, right? How to draw the DC load line. So the line which is drawn between the saturation and cutoff region is a DC load line. So in order to draw this DC load line, one should have this equation. How do you get this equation? By applying KVL to this output circuit, because we are studying the output characteristics, so we apply KVL to the output circuit, okay? So you can see IC is equal to VCC minus VCE by RC. If you split up this equation, this is what you get two terms, and this is the slope of this DC load line, and this is the magnitude VCC by RC. This is the maximum possible IC current. This point is actually VCC by RC, right? And this is the maximum current and this is the lowest current, IC, right? So once you get these two points, okay, on x-axis and y-axis, then if you join these two points by drawing a straight line, okay, then it is called as a DC load line, right? This is called DC load line because now the circuit is working under DC condition, DC biasing is done, right? And this line, slope of this line depends upon the load, that is RC. So that is why it's called DC load line. So once you have this, okay, once you draw this, wherever the intersection of DC load line with the output characteristics for different values of IB, those points are called as quiescent point or operating point of a transistor. Okay, it is not like this, it is only for the understanding purposes we have shown these Q points. It is not like this, okay, right? So you need to draw the DC load line so that you get a Q points, right? If you are doing some experimental analysis, okay, you need to do this, right? So placing Q point somewhere in the active region is not our job, okay? It will not stop there. So in this active region, where exactly you want to place the Q point, whether you want to place Q point here or here or here, or you need to choose a proper Q point. Do you want Q point here for amplification, or you want your Q point to be here for an amplification, or if you want Q point in the middle of the active region or on the DC load line, okay, that is what you want. So that is where a designer role plays very important part, okay. What happens if you place Q point here, here or here? So we will see that next, okay. So at any point of time you can only have one Q point. Please remember, don't get confused, okay. At any point of time you will be having only one Q point, right? These different Q points we get because of different IB values, okay, right? Okay. You can choose any one of them, and you can definitely choose any one of the cue point, right? So here um, here you can see, yes. Now assume I considered IB value as 300 microamperes, right? If I am not considering 200 and 400 microamperes, means I am going to apply VBB such that I am going to take RB such that the current flowing through the base of the transistor is 300 microamperes. That means it is the middle case, right? This one, the case 2. Take this case. I am going to take 300 microamperes, right? So if it is the case, so I am going to get this curve, this output curve, right? Middle one. So when I draw my DC load line by applying KVL and all, so when I draw a DC load line, somewhere here it intersects, and this becomes my cue point. So now I'm going to apply an input voltage, AC input voltage, right? After doing some proper biasing, you need to apply AC input voltage, right? This is the restriction, how much voltage you should apply for a given transistor, for a given amplifier. Okay, there is a maximum limitation, maximum limit for an input voltage. This is an alternating current, it's an AC signal. Okay, right? So combination of this is applied to the base of the transistor. That is how amplifier works, right? So this alternating current or this AC signal varies on the DC input signal, right? So this is the cue point. This is where I am going to apply my AC signal, right? So this is called IB, small suffix b, IB. Okay, this current is due to this analog input voltage. Okay, and capital IB, it is only for biasing in order to fix the cue point. Now I am applying an AC input signal, okay, for this. So this is what the output voltage I get, and this is the amplified version of the input and 180 degree out of phase, okay, and also the collector current. See the change in collector current. This is the change in collector current. Okay, right? There is a swing from 30 to 40 and from 30 to 20 during the positive and negative cycle. Here also, this is the swing what we get, right? So what happens if you choose this cue point somewhere here or somewhere here? How to choose cue point? By changing the value of IB. If I am going to take IB value as 400 or IB value as 200, what will happen? So see that. Let's see that. Okay, so this is the case where I have chosen a value of IB as 400 microamperes. 400 microamperes. So cue point is not in the middle of the DC load line. It is above the middle of the DC load line. So when you apply an input signal, something like this, see, input is itself is clipped off here because this cue point is very close to the saturation region, right? So definitely output is also clipped off. Collector current is also clipped off. So it is not a faithful amplification. You are not getting a original shape of the output signal, right? So on the other hand, if you place or if you consider IB equal to 200 microampere, so this is a scenario where you have a cue point just below the middle of the DC load line. Okay, it is very close to the cutoff. So if you apply input voltage something like this, so your output voltage is clipped off. Current, you can see this is not a faithful amplification. Or on the other hand, so you have a cue point exactly at the middle of the DC load line. Okay, exactly at the middle of the DC load line, but still you are getting a clipped output voltage just because there is a limitation for a given transistor amplifier. Okay, how much input voltage you can apply, right? So by looking into this is the ideal case. Okay, so this is the saturation point and this is the cutoff point. So I can apply an input voltage till this level, still this level. Okay, not beyond that. Say assume it is 50 millivolts. Okay, if you go beyond 50 millivolts, say 51, if it is 51 now, okay, plus 1 millivolt, this is 50 what it should be, but if you are applying 51 millivolts, okay, it crosses its limit. Output, you get a clipped output, both in negative as well as positive signal. So this is not a faithful amplification. So what it tells, okay, uh, transistor amplifier is also having bindings, right? One need to apply an input voltage, say for example less than 50 millivolts. Okay, for less than 50 millivolts this circuit works well and it gives a faithful amplification. Okay, so with this I'm going to conclude this lecture. Thank you.